and then I'm gonna give her
The big intro.
Okay.
Perfect.
Hi.
I'm glad you noticed that.
Thank you. Yeah. Yeah, I understand. Yeah. I'm so glad that yeah, okay, I'm sorry. And I saw Miriam, and she's
Marty, are you okay with pictures?
yes.
Just to know.
You are, okay. Yeah. Fern's going to start us out. Okay. She's going to open this. Fern's going to start us out.
Do you need to have this on, or?
I'll wait till
Oh, okay.
it's
Shall we get?
Great, bienvenidos, welcome everyone. I want to give a very brief welcome. Thank you to Dr. Marjorie Chan, who's going to be speaking to us about her research today. Thank you for sharing your knowledge and enthusiasm for this subject with us. And also thank you to Jack and Melanie for all that you bring to Monteverde, including your very interesting friends, and for always encouraging these spaces for us all to learn and get to know something about a new subject, at least for me. And thank you to everyone who is here in the audience today, because that's a huge part of making this happen. All right.
Thanks, Fern.
okay. Before we introduce the speaker, we're going to introduce Club Moss. And this is the Club Moss team. And this is the first post-pandemic episode of Club Moss. And so what Club Moss is in honor of a woman who lived for many years here in the community named Martha Moss. And she was our neighbor. And she was an amazing, wonderful person. And she became elderly and died. And we now actually live part-time in the house that was Martha's home. But we decided to start, we were in the habit of inviting friends of ours down to stay with us for periods of time after. And so we actually started this thing called Club Moss. And the idea was we would invite some of our friends to come and stay with us in Monteverde, and they would get free lodging. And in return, they would have to give a lecture to the community. And so we had several prior to the pandemic, and now we are, after a several-year hiatus, we are cranking up Club Moss again. Now, a feature of Club Moss is that there is a private, catered, small group dinner with the speaker. And attending that dinner is by Laura. And it is next Monday night. And what time do we decide? 6?
6.
Next Monday night at 6 at our house. And the way this works is that during the talk, we'll pass around this sheet of little papers. And if you would like to be considered to attend the private dinner, you write your name on a little piece of paper. And I guess we send a can around.
Yeah.
We send a can around. And you put your name on a piece of paper and put it in a can. If you are a couple, you may write 2 names down and put a piece of paper on 2 names. And then after the talk and after questions, we have the drawing. And we shuffle them and we pull out slips of paper until we have 6 guests. Understood? Well, this one still has a name on the back, I have. If you see a name already on a piece of paper, get a different piece of paper.
Scratch out the name.
And with that, I'm going to turn it over to Lee to introduce our speaker.
Thank you. I am delighted to introduce our friend, our colleague, and a superb geologist named Marjorie Chan. She's a distinguished professor of biology at the University of Utah. She received her BS, her bachelor's degree, in science at University of California, Davis, and her PhD in geology at University of Wisconsin in Madison. Over her career of 3 decades at the University of Utah, Margie has had a very active research, education, and public engagement career. Her research has spanned some of the Earth's oldest rocks, Precambrian, and some of the youngest rocks, the Pleistocene rocks. She runs the STAR Research Group, which stands for the Sedimentary and Terrestrial Analog Research. And this work applies to understanding the geology of Mars and planetary sciences through understanding processes of geology on our planet, on planet Earth. She has published over 117 peer-reviewed articles, and her research has also been featured in National Geographic and the Discovery Channel documentaries. Now, Marjorie also has a lot of interests outside of geology, and she weaves these interests into her science. She was the department chair for 7 years in the Department of Geology, and she oversaw the development and programming and new construction of our geology and geosciences building. It's just an amazing building because she has interwoven aspects of geology with art and the aesthetics of the beauty of rocks. And so it's been called one of the most spectacular earth sciences buildings in the country. She's also very interested in helping women in geology, and she created a prize-winning video called Women Who Walk Through Time, which shows the work of women scientists and encourages young women to understand the importance of careers in geology. So with that, I'll turn it over to my dear friend and colleague, Marjorie Chan. Thank you, Marjorie.
I'm really excited to be here. This is the first time we've been to Costa Rica, and it's really fun because geology has allowed us to travel all over the world and see just fantastic places, so we're so happy to be here. I'm going to talk about red rocks, which is a lot of the landscape in southern Utah. And one of the things that is really serendipitous is sometimes things just happen in science. And this was one of those things where I just kind of fell into something. I had been taking people out looking at some of the red rock country in Utah, and somebody said to me, "Have you ever thought about whether this red rock in Utah relates to the red rock on Mars?" And I said, well, I've never even thought about Mars. And from a really great collaboration, we were able to come up with some ideas, and then we were able to see those ideas actually tested by some of the rovers that went out, and it really was one of the highlights of my career. Very exciting. So today I'm going to talk about 4 different things. First, I want to talk about perceptions that we have and how our perceptions change. And then secondly, I want to show you how we use analogs, or how we use Earth examples to actually interpret the geology of Mars. And then the third thing I want to talk about is where our science is going to go in the future. And I think this is really interesting. And then the fourth aspect that I want to address is science and art. And I know that some people here are interested in the combination of those, and I found that that also is very helpful for telling stories in a different way. So the first thing is to just maybe pause and think for a minute, what do you think about when you think of Mars? What is your perception? And what kinds of things actually influence your perceptions? And I have a picture of Mars. So we'll see if any of these perceptions that I show you match any of what you've been thinking. But here's one example of a perception. If you're young, you might think of Mars as being something like this. And this is where you don't have a lot of data, you're just a young person. And then maybe as you get a little bit older, Mars takes on a different meaning with this particular character. And then one of the things I grew up with as a kid was watching my favorite Martian. And I kind of had this idea, well, maybe that's the way Martians were, these little antennas coming out. But then as you get older, maybe things get a little bit more sophisticated as you're able to take in more science and combine that with imagination. You might come up with the Martian Chronicles. And one of the things that makes it interesting is that there are these possibilities that some things could be true, and it makes it seem like, oh, maybe that story could really happen. But it just makes it much more fun as science fiction. So we have different kinds of perceptions, and what I want to assert is that a lot of our perceptions are based on data. So here's an example of the face of Mars, and this was from an image in 1976 where people saw this and they were all excited that, oh, there's a face looking back at us on Mars. What we found is that over time, as you got higher resolution and different images, you actually saw that this was not a face. In reality, it was just a natural landform. But the low resolution in that Viking photo actually made it look like a face. So there really wasn't a Martian face tape, so about 30 centimeters. And that difference in the data is actually really changing our perception of what Mars is like and a lot of the geology of Mars. And of course, the rovers have really added a lot. So here you have some of the examples of rovers. The first rover was a Sojourner in 1997, and this was kind of considered the McDonald's of rovers. It was faster, cheaper, and maybe better because it was cheap. And it could get around, but it couldn't really do a whole lot. And so the next generation is the Mars Exploration Rover. There was Opportunity and Spirit 2004, and much of my research related to the things that the Opportunity rover saw. And then in 2012, we had the Mars Science Laboratory Curiosity. That's about the size of a Mini Cooper car. And then the current rover that's exploring now is the Mars 2020 that landed in February 2021. This one's called Perseverance, and it has much more instruments. So what you're seeing is that we're getting more data because the instrumentation is getting more sophisticated. That allows us to collect more data. And one of the things that we're hoping with this Mars 2020 at Jezero Crater is that it actually might cache some samples, and we might be able to bring those samples back to Earth someday. Yeah.
Margie, what's the relative size of that new one, the 2021, relative to the other ones?
This one it's about the same size as this, just a little bit, I think it's a little bit bigger,
Okay.
But it's got lots of instrumentation, and they really kind of have to pack it on. And sometimes it's interesting that they're trying to cut so many corners, make it light enough, etc., that sometimes, for example, the wheels are made so light, and then when they hit the rocks, they get punctured, and they didn't realize that those kinds of things would happen. So oftentimes, you learn from making mistakes, and things are getting more miniaturized, which makes it more effective for some of the kinds of things that we want to analyze. So more data, increasing resolution, that's increasing our scientific findings. So what I want to show you is a perspective, because in some of the old displays of Mars, you can see pictures like this, and this really kind of looks like the moon. It was a red planet, but people thought it was mainly igneous, things like basalts. And what we're seeing now, since about 2004, is that a lot of the deposits on Mars are sedimentary. And so these look much different, and these form in different ways, and in particular, they show a lot of evidence of water. So I want to show you how data and using Earth analogs can make a difference. So to really kind of help you understand the rock cycle, I use cars just because everybody understands cars. And so you can think of igneous grains as being like the car on the left. It's fresh and pristine, and it's really easy to kind of tell what it is. You can think of metamorphic rocks as being like these cars down here at the bottom. This is where meta means change and morph means shape. So there's been pressure that's actually changed the shape of the original grain. And so that's what metamorphic grains look like. And then sedimentary grains, I think, are most like a beat up VW. They are the cars that have been around the world, or have been around for a long time, and they have lots of dings and dents. And to me, one of the fascinating things about sedimentary grains is to actually try to unravel where have those grains been? What's the story from all those dents and dings, etc. And so I'm interested in sedimentary rocks, and that's kind of what the focus is going to be. And I also look at what we call diagenesis. Dia means secondary, and genesis is origin. So we're looking at secondary things that happen when the grains come to rest, or in this case, when the cars were actually parked or when they were actually came to rest. So you can see that there's moss growing on the car. And so that is something that's still part of the story, but it's something that happened a little bit later. And so much of what I'm going to be talking about today is about diagenesis in sedimentary rocks. Okay, so the second part, besides the perspective, is to actually look at some of these examples. So we're going to go from Earth, and then we're going to take what we know from Earth and take that to Mars. And I'm going to tell you a story about diagenesis, which are the secondary things that happen. And a lot of what we see in the red rock country, a lot of this coloration that you see, and some of these beautiful colors here, and even these balls that you see here, these are related to the story of how iron, the element iron, has actually cycled through the Earth's crust. And I like to think of Mother Nature as being an artist. And if you took the artist palette, iron is really what makes up a lot of the artistic palette of the rocks that you see, the sedimentary rocks that you see. There's a lot of reds, whites, yellows, pinks, oranges, and it's quite vibrant. So I'm going to tell you the story about diagenesis and how iron cycles through the crust. Now, we're going to look at what we call concretions, and geologists call these things concretions because these are cemented mineral masses in the sedimentary rocks. And these are from different fluids, and they can be waters. Maybe you wouldn't want to drink the waters, but we use the term water, that have actually seeped through the deposits or seeped through the rocks. And they actually cement them together. So here's some examples of concretions in shale. These are some examples of concretions in the sandstone. And if you were to look at this in a thin section, just like in biology where you can make a really thin piece of the material, and you can put light through it, you can actually tell different properties. So the concretion is actually cemented together, and these are some of the quartz grains here. And the host rock doesn't have as much cement. So the blue are the holes, or what we call porosity. So you can see there's a big difference between the host and the concretion. So the concretion is cemented, and that makes it hard, which makes it stick out like that. For a lot of geologists, concretions have been considered just oddities. Most people don't pay that much attention to them, but I got very interested in them, and I was looking at some of the examples that are on the left. And I just want to point out that concretions actually are also these kinds of shapes that are on the right. And literally some of these can be tens to hundreds of thousands of dollars just because they're so sculptural. And these are natural forms just from how waters actually move through and cement some of the rock. So even though we think of concretions as being these odd things and some people ignore them, the fact is that they're more valuable than a lot of rocks that you might actually come across sometimes. Okay, so they can be very complex chemically. So when we have cement, this is like glue. You can have different kinds of glue. And so some of those cements are what we call carbonates, which are like a limestone. Some of them are pyrite, which is like a fool's gold. And then we have azurite that makes these blue, malachite that makes these green. And these kind of brownish, dull-colored ones are the ones that I've been interested in, the ones that are actually cemented by iron oxides. So the diagenetic colors are reflecting how iron is moving through the rocks. And in fact, these concretions, these cemented mineral masses, are actually marbles that are from how groundwater has actually flowed through and cemented different areas in these round balls. And of all the units that are on the Colorado Plateau, where we have just fantastic geology exposed, the one unit that's the most porous, or the most like a sponge, is the Navajo sandstone. And because it's very porous, what happens is that fluids have moved through there more easily than they would move through some of the other units. So this is the unit that contains some of the greatest variety of concretions. So in the story of how this works, you probably start off with getting sand grains that have a very thin coat of iron oxide fairly early on in the depositional history. And it's just like a real thin coat around the grain. But then when these deposits or these sand grains get buried, you have some waters that actually come through and they can bleach the sandstone white. So you can actually see the rock there, and you can see the coloration change just because certain fluids have come through, and it's almost like bleaching a stain out of your clothes. That's a different chemical reaction, but the idea is very similar. And then so what happens is that the iron is removed, and then later the iron gets precipitated back into those little compact balls, or what we call the concretions. So the iron goes from being very dispersed to then being very concentrated into these balls. And the kinds of fluids that are responsible for bleaching the sandstone could be things that are chemically reducing, like petroleum-rich fluids. It could be methane. You could have organic acids. You could have acid, just regular acid-rich waters. Those are things that often actually bleach the sandstone. And this particular example, this is called the white rim sandstone in southern Utah. It's all white, and there are places where you can literally see the hydrocarbons dripping out of the outcrop. So it's kind of like the closest to the Beverly Hillbillies that I think that I've ever seen. Okay, so just to kind of show you a little bit about how this works, I've got this little movie. So you start off with red sand grains that have those coats on it. Then you have some infiltrating, reducing waters that bleach the sandstone white, and they are essentially dissolving the iron and putting it into solution. So the waters then are rich in what we call Fe2+. And then when you introduce other types of conditions of oxygenated groundwaters, that actually changes the chemistry and causes you to precipitate that iron that had been dissolved out. And so then it goes into those little balls that we call concretions. So this is just kind of the basic model that we've developed over looking at literally hundreds of concretions. So now what we want to do is take that knowledge and apply that to the red planet. And so on Mars, they knew that there was the mineral hematite, which is Fe2O3, that's an iron oxide mineral, and they knew that it was present from some of the remote imaging that they were able to do. And so they decided to send one of the rovers to an equatorial area that was called Meridiana Planum, and they essentially said, most of the time hematite forms in the presence of water. So if we essentially follow the water, if we go to the minerals that were formed in water, maybe we can find extraterrestrial life. So the idea was to follow the water potentially to life. And they were thinking that the iron would be distributed like this in layers. And those banded iron formations are fairly common on Earth. But right before the rover actually landed, my colleagues and I actually proposed that maybe the iron would be distributed something like this. And so it was really exciting to actually see that become a reality once they started sending some of the rover images back. So the rover landed in a crater, it was called Eagle Crater. It was just a little small crater in this area that they knew had the hematite. And they called it Eagle Crater because it was like getting a good golf shot. And the rover was in a balloon, and so the balloon kind of bounced and landed in this little crater. And then when it opened up, it actually took some of these pictures. So this picture here at the top shows one of the early images of the crater walls. And it shows the thermal emission spectroscopy that's superimposed on the image. So essentially, the high amounts of iron are shown in the red color that's superimposed. And then the light color is where there's low amounts of iron. And then where it's the green and the blue, those are intermediate areas of iron. And these are actually where the rover balloon bounced and kind of pushed some of the iron into the Martian soil. So you can see how the distribution is similar to this. This is the area that would be like the red, where you have high amounts of iron. And then these places where it's been bleached white would be like the areas that had low amounts of iron because of reducing waters that actually went through. Some of the things that were most interesting is when they actually got close to actually see where was the iron in the rocks. So the images that are shown here on the left, this shows a rock that's in place, and what they did was they applied false color. So the yellow is just showing where the iron is just to make it stand out better. And what you see is that the iron is in these little balls, these little spherules, and the iron balls aren't really touching each other. They're actually kind of physically dispersed. And normally in geologic settings, grains are next to each other. Or if you go to a riverbed, you know, all the cobbles are kind of next to each other. So it's unusual to have things actually dispersed. And so if you could see these spherules with your naked eye, it would look like this steel blue gray color. So they decided to call these blueberries because it would look like a blueberry with your naked eye. And then the other thing is that in the outcrop, they're kind of dispersed like blueberries in a muffin. So those blueberries on Mars actually show a lot of similarities to the things that we see on Earth. And so we actually use these Earth examples to say, we see these similarities, so this is telling us that there have been groundwaters that have actually been moving some of the iron and redepositing it as those concretions or those spherules. So that was really exciting. And what we would see that there'd be lots of similarities. So you can see that on Mars, they had some of the spherules were what we call conjoined forms. They would be doublets or they would be triplets. And some of them actually had ridges on them. This one's just poking out right here. And the ridges you can see even occur on examples on Earth. And so whenever there's just a little bit of difference in the texture or what we call the porosity of a layer, sometimes you'll develop these, this preferential growth along those layers, and sometimes they'll actually look like flying saucers, just because the middle part is got more permeability or more porosity. So on Earth, what we see is that we have a variety of shapes. We have things that are doublets, we have triplets, we have spiky balls, and these are some of the examples. These are about golf ball sizes, and the smaller ones are much more common. And so the ones on Mars are about this size right here. And so they're small, they're about 4 millimeters in diameter. But as they've been exploring more, they've actually found that there are many more sizes, but not as big as what we have here on Earth. So one of the questions is, why do we have so many more sizes and so many more shapes on Earth than on Mars? And so my son is standing on one example here that's like a beach ball. This is out of area near Las Vegas, Nevada. And these examples over here, this is one of my favorite locations in Utah where these are all about the size of grapefruit. So they're actually quite big. Some of the small ones are much more common, and when you're out, it's kind of like the movie Home Alone, where the bad guys slip on those ball bearings. And it's kind of like that when you're out doing the research. But I want to assert one of the reasons why it might be different is that Earth is probably contaminated with life. So when you think about these being products of water, so much of our water for the last 3.5 billion years has had microbes in it. And probably those microbes actually do something and they enhance the ability to precipitate things. And so in some ways, we might not even really know what abiotic looks like. What does a plant look like without life? Or what do certain minerals that are not influenced by life, what do they look like? It's really hard to know because everything that we look at is just so permeated with life. So that's a challenge. We see that the cementation can occur quickly if the conditions are right. So here's an example of a pocket knife. We know a pocket knife is maybe 100, 150 years old. So we know that that mass that's cemented around it had to be less than 150 years old. And here's a watch band, and the same idea here is, maybe this is 40 or 50 years old, and this mass that's cemented around it, probably because there was some iron that it was attracted to, that's also happening fairly quickly. And we know that these are waters, modern waters have microbes in them. So that's something to keep in mind. Now, this brings me to a topic that is one that has been very much of interest to astrobiologists, and that is, how do we recognize whether things are influenced by life? And how do we find biosignatures? How do we find the actual signature that life was involved? And is it visible or is it invisible? And most of the time, if it's invisible, we consider, well, then it wasn't there, it wasn't involved. But just because it's invisible doesn't mean that it wasn't involved. It just means that we can't see it, or that we don't have the instrumentation to detect it, but that doesn't mean that it wasn't involved. So I want to take one mineral like pyrite. This is fool's gold. And we have these examples on the left, and those are ones that people would say, oh, those are abiotic, those don't have any life involved. But if you actually look at some other examples, well, you start seeing what we call rhomboidal pyrite. It's kind of more irregular looking. And then I'm actually sitting on another concretion that's pyrite. That's from China. And then here's a fantastic example of a crinoid. This is like a sea lily, a fossil sea lily, where all of the lily parts have been replaced by the mineral pyrite. It was originally a carbonate mineralogy, but it's been replaced by pyrite. So what you would think is, on the left side, no life. On the right side, there is life. But there is probably a gradient, and maybe the stuff on the left just means low life. Doesn't necessarily mean no life. It just means maybe we can't tell, or maybe we can't detect. So there's probably a continuum. And these are some of the things that people are going to be looking at more in the future, like how can we develop better instrumentation, or if we don't have DNA, how do we tell whether life was present or not? So life is everywhere on Earth, and for geologists, we're realizing more and more that it's inseparable from the geology. Life is intertwined, and even in this cave, there's just this little droplet of water. And this little droplet of water is full of microorganisms. And those microorganisms are contributing to the precipitation of the stalactites, etc. So think about that life really is influential. And when we look at Earth examples, we have this bias because we are a water planet, and we're just an example of n equals 1. But in fact, we have to kind of remember that we've got that bias. So we're looking at other kinds of examples of water, and here's another one of my study areas. And this is a drone image looking down at more of the Navajo sandstone, this unit. And what you'll see in this drone image right here is that there's all these swirly patterns. And those swirly patterns are a function of having water-saturated sediments, and probably something like an earthquake where it shakes it, and then the layers just get deformed from all that energy. And we can use, again, this example as an analog to Mars. And you can see here, this image on Mars has these same kinds of swirly patterns. And that's probably also indicating that there was high water table conditions on Mars, and maybe some Mars quakes that were actually contributing to getting those kinds of patterns. So, other examples of how we use analogs. Here's the weathered landscape of some of the Navajo sandstone in southern Utah. And what you see is that it's covered by these polygonal types of cracks. And these are actually weathering cracks because they actually cover the whole surface. And it's telling us about how much time the surface has been exposed to the elements. And on Mars, they also found similar types of things. You can often see that there are smaller polygons within larger polygons. And so again, we use these Earth examples to say these are telling us about how the rock actually accommodates different conditions, could be like temperature differences, and how it facilitates some of the stresses. And also, some of those cracks could be places where life goes. So particularly on Earth, those cracks are places where water is going to go, and so those are preferential sites for life. Okay, so the third topic that I wanted to talk about was where are we going in the future? And the thing that's very exciting is the use of cyber technology, artificial intelligence, and how that is going to change our science. And over about 10 years ago, I was involved in a team that was actually trying to address the idea of having something like a Google Earth, but having all the science data accessible on some kind of a GIS or visualization platform. And Google Earth said, we are not interested because we don't see us making money off of that. But this was something that was going to definitely continue into the future. And there is Google Mars that does have some information, but really artificial intelligence is changing how we do the science and maybe helping us advance the science by enabling us to do things and look at relationships that really weren't possible before. So NASA recognized that it was important to have these visualization platforms. So they've actually developed what they call the solar trek systems. And so for each planet, each planetary body, they've developed a GIS visualization thing that's a little bit like Google Earth, where it just has all the science data as well as some of the types of things that we would use related to the science. So I wanted to show you how this would work and how it would be nice to actually have this going forward in the future for Earth as well as other planets. So this will have a little bit of music and I hope I can talk over it. So here's the Mars trek and how it works. So you can actually go in and pan and zoom just like you do on Google Earth. You can go into certain spots and you can see what data were collected from all the different missions that have actually been there. And since the data is only about 50, tens of years worth, it's not too bad to put it all in one place. You can look at some of the highest resolution data. This is from the high-rise imagery from the Mars Reconnaissance Orbiter. And then you can actually do calculations. You can actually draw a line and get an instantaneous profile. And it would be nice to look at the layers that were underneath the profile. You can look at where the orbiter currently is and where it's actually imaging, so you can see that it gives the lat long. And you can also go in and select the area, and you could actually print this terrain out on a 3D printer. And this technology has been available for several years. They also said, we can integrate the Curiosity rover data and put it all in this format, and we can actually put bookmarks, just like you would putting pins in Google Earth. And then we can make this relate to what people in popular culture see. So this movie that came out a couple of years ago, The Martian, was actually translated to this platform where they actually showed all the sites that Mark Watney would have visited and had to go through to get picked up and rescued. So it's really going to be an exciting future because it's a platform that everybody can participate in. And you can integrate the popular culture as well as the science data. And of course there will be review processes and other types of things to validate whether certain data should be allowed or not. But I think this is really going to be something in the future. Okay, so the last thing I wanted to talk about are building connections. Oh, yeah, question?
Just really quick, does the instrumentation on James Webb help you in any way?
Not so much. I mean, that helps actually get a much bigger picture of all the things that are out there.
But maybe up close and...
Yeah, but these are just focusing on some of the planetary bodies where we have lots more data. But who knows, things are going to change in the future, and it's really amazing what they've been able to find with those telescopes. Yeah, thank you. Okay, so I was really fortunate to be contacted by this artist from Amsterdam, and she said she was interested in the sandstone colors, and she wanted to come out in the field with me, and I said, great, let's go out. And we went out to this area that had both colors as well as some of these concretions. So I didn't know exactly what she was going to do, but she was very quiet, just made lots of observations, and came up with her ideas of what she was going to do. And it really kind of surprised me because what she decided to do was to take a certain area of the natural landscape, and this is in a monument where you can't take anything. So what she did was she took an area and she measured all of the concretions that were in that area, and then she plotted them up on a map. And then what she did was she experimented with clay, and she physically reproduced the size and the texture of those concretions, and there were over 500 of them. And it was quite a job to actually kind of get things right, and then she laid them out in the position that she had actually measured and such. And it really spoke to me because it showed me how different people see the landscape with different kinds of eyes. And I was able to do a Zoom when they had the gallery opening and talk a little bit about the science behind it. And people were fascinated, and they had some great questions. And to me, it really showed that if you integrate science with art and with other disciplines, you can actually share the story in a thoughtful way that's inspiring, and it really can evoke new conversations and new perspectives that can contribute to our understanding and appreciation. So this is the display. She called it Here and Everywhere. You can see her with all her concretions and the experiments of different colors and different textures, and we're actually hoping to get this at the Utah Fine Arts Museum so it can kind of come home in a way, because it's only been shown in Europe so far. Okay, so to summarize what I've said today, I hope I've been able to show you that there were 4 main things. Number 1 is that red rocks on Earth as well as on Mars are telling us a story about how waters have moved through, iron-rich fluids in particular, and how they actually influence the crustal areas of both Earth and Mars. Secondly, I hope I've showed you that we use Earth analogs, or we use Earth examples to tell us about concretions, as well as even some of the features like we call soft sediment deformation, these swirly patterns. And those are telling us about watery conditions on Mars. So these Earth examples actually did really solidify the idea that there was subsurface water on Mars. Before, people thought, oh yeah, there's surface water, but they hadn't really thought about the subsurface water. And that's what these analogs actually can help tell us. A third thing that we need to understand is that when we use Earth as an analog, there's a bias. And that bias is that Earth is permeated by life. And so that might influence how we view things. And then the fourth point was that data and technology are going to help us make new kinds of discoveries. And I'm sure that things will develop in ways that are kind of unexpected because of data and technology. And then the fifth idea that I hope I've left you with is that it's just really great to share stories and to actually learn from the interactions of different perspectives that people have. So the future is very exciting with lots of frontiers. Earth and planetary science have merged together in ways that weren't present, maybe 20 years ago. And for me, I think it's really exciting to look forward. And I put this here because really it's the next generation that's going to actually be able to explore and do things that my generation never even knew was possible. So for the new generation, and I think there is at least one young person here, or was here, their responsibility is to protect Earth and its heritage and explore new worlds. So thank you very much. Any questions? Yeah.
Would you expect to find similar attributes in other planets in the solar system? I mean, we never see a nice, neat image because it's clouded, and what do we know about some of the other planets?
Well, a lot of the other planets are kind of overwhelmed maybe by other types of things, by gases, right, or, So Mars is the one that's kind of most like Earth, the rocky type of planet. But people are kind of keeping that in the back of their minds because you never know. And people are actually looking at, well, can some concretions actually form in situations where there's, let's say, volcanic gases, and will they actually influence things in similar ways? So, I don't know what the answer is, but I think people are trying to have open minds. And just the fact that we were able to take some of this to Mars was a big step, but there are lots of other big steps that are going to come. Yeah, thank you.
Thank you.
Yeah, Elaine?
So what is the time frame of when water was on Mars?
Oh, gosh. That's a good question. When was water on Mars? A lot of the areas that it was exploring is an area that's an older terrain. And This is a terrain that they call Noachian when there were floods, and they think there were floods in surface waters. And a lot of that is fairly early, like 4 to like maybe 2.8 billion years. And then it seemed like a lot of the water just disappeared. And so one of the big questions is, you know, both Earth and Mars seem to have water early on. What happened to the water on Mars? And so some people think that there was all these solar winds, and the solar winds kind of blew it away. People also have talked about the idea that Earth has got a magnetic core, you know, that actually kind of influences its ability to hold an atmosphere and do other types of things that Mars can't do. So a lot of it's still unknown, but it seems like a lot of the water history on Mars was early, and then most of it has stopped. It hasn't totally disappeared because they actually can see things that are streaks, and they seem to be related to seasons, and it seems like there's some ice that's actually in the subsurface, but most of the surface water is gone.
Thanks.
Yes?
Is there a magnetic property to the iron that propels it and keeps it from clumping together? Or that makes them so evenly distributed?
Oh, that's a good question. Yeah, what makes them evenly distributed? And that's something that people often ask. I don't think it's a magnetic property, but it's kind of hard to explain. But some things in nature have kind of a self-organization. And sometimes you actually even see it in landscapes where there are bushes, trees, or there's sort of a spacing. And they have kind of this nearest neighbor area, and they say, you know, this is my terrain, and the next tree is spaced out. And so there is some kind of this self-organization to these concretions. And I also tell people, you know, you can think of it as being like musical chairs, where people are the iron. I don't know if you've ever played that game, but people circle around the chairs, and when the music stops, you know, they have to kind of sit down. And what you see is that when there's a lot of people, the circle is bigger. When there's less people, they get closer to the chair, and the circle's smaller. So I think a lot of the sizes and the spacing is related to how much iron is available, and there are probably some natural things, whether or not we can see that there's a nucleus or not. There's still probably some biological components in the microbes of the water and how they're dispersed that might contribute. So that's a great question, and I wish I knew the answer, but something.
They won't answer for us.
Yeah. Yes.
I have a question about scale, because with when they first discovered those black smokers, I mean, that was sort of a game changer.
Yeah.
We didn't think that we would have chemosynthesis, photosynthesis. And with, when you look at the way things, the elements are created on Mars, because of the size of the electrons and nucleus, is that just basic so that it would be possible for anything to be like a completely different size scale, like nanoparticles, whole nanoparticle world on Mars, or is anyone looking at? Is that just a possibility?
That is a good question. I mean, people have actually wondered, you know, could there be different? Could you have life in a different kind of system than what we have and what we're used to? And the answer I think that most people come to is it's possible, but we just don't really understand it enough. And there's kinetics that are involved that we might not understand. So I would say I don't know what the answer is to that, and I know that people are looking at things, and sometimes they're finding unexpected things. And even in the biology department, there's one team that's been looking at areas that are near black smokers and looking at some of these very iron, magnesium-rich rocks and actually finding some evidence of DNA or what they think is actually preserved in those rocks, which was surprising because, you know, I would have thought, you know, there's nothing going to be preserved in those rocks. So we don't know that. And I guess another thing that I have found really interesting, there's some work by Bob Hazen, who is at the Carnegie Institute, and he has actually used big data to look at minerals. And what he's found is that there's like about 200 minerals on the moon. There's about 400 minerals on Mars, and there's like over 5,000 minerals on Earth. And so one of the questions is, he looked at all this big data and did all this, statistical analysis and stuff. And the idea that he came up with is that the minerals on Earth have actually evolved with the evolution of life and plate tectonics and other types of things, and that there's a very close relationship. And so one of the reasons why Earth has probably so many more minerals is because of how life is just intertwined and intermixed, and it actually causes, it's sort of like the evolution of getting different kinds of minerals just because life is involved. And I found that really fascinating. That was like really a new discovery because of data, looking at data and being able to parse it out in ways that people hadn't really thought about before. So I think it's possible that people will find out more and they will realize more. I don't know, on the atomic level though, what those implications are. But it's a good question for the next generation. Yeah.
This is so fascinating. I'm curious what you're hoping to learn from the studies that you're doing on Mars.
Yeah.
One thing that you're dying to learn.
Well, I think everybody wants to know, is there life on Mars? And because it's a planet that is close to us and it has a lot of the water properties and all those kinds of things. And so far, it seems like as a science community, people are being very careful. And even though they'll say some things are lookalikes, you have to be really careful before you make that big claim that you found evidence of life on Mars. So it's been very slow, and I don't know if and when it'll happen, but it'll be interesting to actually be able to bring samples back from Mars back to Earth, because we can analyze them in ways that you can't do, on those rovers. Those rovers just they can do a lot, but they can't do everything. The problem will be making sure that there isn't contamination. So there's going to be challenges, and we'll see how they deal with them.
The life on Earth, molecular complexity seems pretty high. Do we have like a threshold of at what point, like number of atoms or whatever, at what point it starts to look like there's like a real sense for that?
Yeah, that's a good question. And it kind of relates back to this idea of biosignatures. Like, what exactly is the standard for abiotic versus biologic? If we see things that are obviously a fossil, or we find DNA or whatever, we can say that that's life. But is there anything that tells us for certain that it's abiotic? And so people have done things like in the lab, and we know that like at high temperatures, igneous kinds of conditions, we think that's too hot for life. But there's a big range and things cool down, and so at what point does life get involved? So I think the answer to your question is a lot of these things we don't have absolutes for. We don't have a cutoff, a known cutoff. And it's usually end members that we say, well, we think it's at this end, and we know for sure life is involved where we see fossils or these other lines of evidence. But there's a lot of areas of gray, and that'll be the challenge to figure out. Yeah.
I was intrigued and sort of blown away by your statement that the tires of the earlier rovers got punctures. Like, why didn't they test that out in Utah?
Well, they did test it out, but I guess, we... Yeah, they were trying to...
do they test these things out?
Yeah, they do test them out, but maybe there were a lot more sharp rocks, and sometimes I think, things happen slowly on Mars, and they are going over these things very slowly. And when you do studies on Earth, you don't want to wait a year to find out what it's going to do. So you kind of make these projections, or you think, oh, well, it worked like this for, 2 weeks, so we think that's going to be good. It's this combination of engineering and other things. But we had a friend one of our family friends actually worked at JPL, and they were telling us the story of the tires. It was something. Yes?
I was wondering if the gravity difference, is the rover way heavier on Mars because of the difference in gravity?
Oh, no.
I don't even know what the. No.
Yeah,
It would be lighter.
yeah. I don't think that really plays into it. It was more, I think, the rocks, that they were hitting some sharp
Yeah.
rocks. And,
I'm thinking that would be something that would be hard to test. If
Yeah.
gravity's going to be different.
yeah, yeah. But they do test it out. And in fact, in Utah, there's an area that's called the Mars Habitat. That's by Hanksville, Utah, which is kind of this remote area. And they take the rovers out and they test them out. So.
Are there plate tectonics on Mars and other planets?
Are there plate tectonics on Mars? That's a good question. The answer is sort of like life. People think that it's possible, and they've found things that look similar. Like sometimes there's lineations, and they say, "Oh, this looks like it could be a boundary," but there's been no direct evidence of plate tectonics on Mars so far. Yeah.
So how deep have you been able to penetrate Mars in terms of what layers are? And I'm, thinking that, well, if there's uplifting or something like that, then you might be able to see some of these sedimentary layers. Yeah. But, can you tell what's below?
So far, we can't really tell what's below. They can do some things. In fact, I forgot what the name of it. The name is just slipping me right now. But there is a mission that was through the European Space Agency and some partnerships where they actually have a unit that's actually doing measurements for seismic types of patterns, and they can actually see, what some of the things are underground, but it's not the level of detail that we usually want from looking at kinds of examples on Earth. They do have these craters, though, and that's often where they're going to explore, because the craters are areas where there's been excavation from some impact, and so that's actually showing the layers around. And some of these craters actually are filled with old delta deposits and things like that, so they're able to actually take the rover out there and look at some of these cross sections of some of those kinds of deposits. So they can get a little bit of an idea, and then some of the samples that they're taking, they're actually drilling down to get some of the samples, but they're not going, deep. Really deep. Yeah.
And do they know if there's a molten core as a part of Mars, like Earth, or do they suspect otherwise?
That's a good question. I haven't really been keeping up, but I think most of what I heard was that they don't think it's like Earth, where it has a molten core. And that's probably why it doesn't have the magnetic poles and everything else. So, but could it have had something in the past that just died for whatever reason? Don't know. Kind of like the water.
Well, do any of the rocks show any magnetism?
Do any of the rocks show any magnetism? Well, there's certain minerals that are magnetic.
Right, but
so,
I mean on Mars, so that they would line up.
Oh, so they would line up with the poles. I don't think they've been able to do that, and I think that they probably don't have the instrumentation to be able to measure that yet.
All right. Thank you.
That's a good question, though.
Thank you so much.
Thanks for having us.
Thank you.